Hello everybody and welcome to the third and last part of the section on graph sketching. If you're fed up of this, well, it's coming to an end, I can tell you that much. Well, this is part 3, so the third of 3 parts, and we're going to devote this video to the study of asymptotes. What is an asymptote? Definition: what is an asymptote? It is a line towards which the graph of a function approach, towards which the graph of a function approaches. So it approaches the asymptote without touching it, without ever touching it. That is almost always true. We're going to see that there might be some exceptions a little later on this week. So without touching it. There are two types. There are two types of asymptotes. Two types of asymptotes. Well, there's actually 3, but we're only going to take a look at 2 of them. The first one is called a vertical asymptote, and the second one is horizontal. There is also something called an oblique asymptote. Horizontal, that's a Z. That looks a little awkward. We're going to fix this. So vertical and horizontal asymptote. This is denoted for short VA. Horizontal is denoted for short HA. All right. So basically, if I were to show you super quick example graphically before we actually get into a more analytical version of this. Here's a vertical asymptote that I'm positioning at -1, and here is a horizontal asymptote that I am positioning at y equals 2. So these are 2 asymptotes that can be part of a graph, and then the graph itself might actually look like, I don't know, something like this, right? Good old rational function or a variation of it. So here, this is your VA, right? This is your vertical asymptote, right here, while this y is equal to 2 is your HA, is your horizontal asymptote. All right, so we've seen that in graphs several times. So let us see analytically how they can be computed using, of course, the help of calculus, since this is the course we're in. All right, let me get rid of that. So let us begin our study by looking at the vertical asymptote. So vertical asymptote. All right, here we go. So what do we got? X is equal to A is a vertical asymptote for f of x if limit as x approaches A. Aha, this is where the calculus kicks in. Vertical asymptote is related to the concept of limit. So the limit as you approach the asymptote of f of x, this does not exist. In other words, if you remember the meaning of D and E, it is when we have a number divided by 0. And if you remember even further, this actually we have associated to plus or minus infinity. So when the limit is plus or minus infinity, which is dne, which is the number over 0, then we actually have a vertical asymptote. Sorry. Good. So perhaps we can actually take a quick look at an example. Example 1. Let us start a little on the mellow side, so 2.5 star. I don't really like this, it's not very dark. So example 1, find all vase, that's a V. Ugh. Find all vertical asymptotes for f of x is equal to x2 over 4 minus x squared. Good. So we have this function and we want to know where the vertical asymptotes are. Well, we're going to actually involve the concept of a limit in there, and we got to take the limit as x approaches some unknown number which actually will correspond to an asymptote if the condition is satisfied. So how do I get that number? It's actually sort of hidden in the function, but I know what to look for because I know that the limit has to be dne, which means that the denominator of the function has to be 0. Do I have a denominator? I do. I do. So when you're looking for vase, what you want to do first is make the denominator equal to 0. So here we go. 4 minus x squared is equal to 0. Difference of squares. 2 minus x, 2 plus x, which will give us 2 answers, so equal to 0, should I say, which means actually 2 things. X is equal to 2, or x is equal to minus 2. Now, that's good. It makes the denominator 0, but remember one thing, when we're looking for vertical asymptotes, you're actually looking for the outcome of a limit. So without testing this through the limit, we will not know for sure if we have an asymptote or not. So I'm going to do a check here, which is more than a check, which is actually a validation of those 2 numbers that I have found that make the denominator 0. So first I'm going to check that x is equal to 2 works. So what do I do to check that? I take the limit as x approaches a, and my a is 2 of the function that I am given, x squared over 4 minus x squared. Now remember, I'm doing this because I'm looking for a particular result. I want the outcome to be dne. Will it be so? Will it be so? Well, let's cheat. That's 2 squared over 4 minus 2 squared. Oh yeah, that's 4 over 0. Check mark. We have validated the fact that x is equal to 2 is x is equal to 2 is in fact a vertical asymptote. What about minus 2? Again, I need to perform a calculus operation. That is the limit as x approaches minus 2 of the same function. And that is minus 2 squared over 4 minus 2 squared. And that is again 4 over 0. Check mark. We're happy when we get undefined here. So x is equal to minus 2 is also a vertical asymptote. So the answer for this problem is that I have 2 vertical asymptotes. They are at x equals 2 and x equals minus 2, and they have been validated through the limit. Now some of you might actually think, do I always have to check using the limit? And the answer is yes. Check out the next example. Check out example 2. You will see why in this example, if we don't validate, then we're not going to get the right answer. exemple numéro 2. Well, for those keeping track, the first one was 2 stars. Perhaps we bring this one to 3 stars. We make a little more difficult. Find all vertical asymptotes for, what shall we have here? F of x, I want it to be a little more challenging, so let it be something like, I don't know, x squared minus 3x plus 2, so, and then 3x squared minus 3x. Okay, so basically, here we go, new function. First of all, what do I do when I'm looking for vertical asymptotes? What must I do? I must actually make my denominator equal to 0. Why? Because I want a limit to be undefined. And the limit is undefined when the denominator is 0. And I have a nice juicy denominator, 3x squared minus 3x égale à 0. I can take out a 3x from this. And what will I get? 3x times x minus 1. That gives me 2 answers. Yes, 3x is equal to 0, or x minus 1 is equal to 0. And then I have what I'm going to call candidates for vertical asymptotes, 0 and 1. Good. If I stop here, I'm going to get part marks, but there's no way that I'm going to get full marks because I haven't done the check. I haven't done the validation of these answers. So to do that, you basically need to go back to your definition and take the limit of these numbers that you have found. These are the values of a. These are the values that make the denominator 0. So check. We're going to check x is equal to 0 first. So we need to take the limit as x approaches 0 of this function. X squared minus 3x minus 2 over 3x squared minus 3x. We plug the 0 in. 0, 0 minus 2, that's the good old cheat, and 0, 0 here. Hallelujah, God is good. We got minus 2 over 0, validation. X is equal to 0 is a val. What about the other one? I'll need a little more space, so I'll go over here. So check. X is equal to what? What is the other value? We said it was 1, so we're checking x is equal to 1, which means this time we are taking the limit as x approaches 1 of my function. And what is my function? Well, it is x squared minus 3x plus 2 over 3x squared minus 3x. All right, so I do my cheat. Let 1 go there. 1 minus 3 plus 2. Oh, 1 minus 1, or 3 minus 3. Oh, 0 over 0. Is that undefined? Is that undefined? It isn't. That is indeterminate. Oh, this is not undefined. So we know what this means. It means more work. 0 over 0 means we don't have an answer yet. We need to do more work. So limit as x approaches 1 of x2 minus 3x plus 2 over 3x squared minus 3x. What could I do to this in terms of more work? Well, remember, algebraically speaking, more work means expand, factor, rationalize, common denominator. Which one will it be here? Clearly, I think we need to factor the numerator. Well, product sum, right? The product is 2, the sum is minus 3. It is very easy. X minus 1 and x minus 2. As for the bottom, I guess I could take out 3x, and I can go x minus 1. Oh, look at that. Oh, look at that. This is now equal to the limit as x approaches 1 of x minus 2 over 3x. I'm ready to cheat again. This is 1 minus 2 over 3 times 1. That's 3. Hey, yo, that's minus a third. This is not undefined. This is not undefined. Not D and E. It's actually well defined. So fail. Aha! So I would not have seen this. This value, x is equal to 1, is not a vertical asymptote. It actually fails. So basically, my final answer is that I really have only one VAW. F of x has one vertical asymptote, and this asymptote is located at x is equal to 0 because x is equal to 1 does not work. So you see the importance of always validating what you have found by letting the denominator equal to 0. Very important in this section. Keep that in mind. Good enough. All right, time to take a look at the second part. So B, horizontal asymptote, HOS, horizontal asymptote. So a little definition, y is equal to b, right? It's not x is equal to something like in the case of the vertical, we are now horizontal. So y is equal to b is a HA for f of x if either limit as x goes to infinity of f of x equals to b. So see the difference? Here, I don't have to find where the limit goes by making the denominator 0. No. I know where it goes. It actually goes to either infinity, and it's equal to my horizontal asymptote b, or limit as x goes to minus infinity, and this should also equal to b. So this isn't really about taking the limit as infinity, and we're good at this because we have done many examples before. Let's call this example 3 so we stay in the same part of the course. Let's bring this to 2.5. Find all HAs for f of x is equal to, well, what about what we had before? X squared over 4 minus x squared. Okay, that's like example 1, but in example 1 we wanted the VAS, now we want the horizontal asymptote. So how do I do this? I need to actually perform two things. I need to perform limit as x goes to infinity of my function. And then when I'll be done, I will have to perform the limit as x goes to minus infinity of my function. So let's start with the first one. Let's see if the first limit actually gives me anything at all. How do you do a limit? We're starting to review for the final exam at this stage of the semester, right? So how do I do a limit? I plug it in. I do a cheat. What's infinity squared? Infinity. What's infinity squared? Infinity, 4 minus infinity, it's minus infinity. Aha, what is that? Infinity over minus infinity is indeterminate. But then we don't have like 4 different tools for this. We have one tool that is we divide top and bottom by x to the highest power. So I am going to divide top and bottom by x to the highest power. What is the highest power of x in x squared and 4 minus x squared? It's obviously x squared. So you know what, let me cut to the chase. So x squared here, and here 4 over x squared and also x squared over x squared. So we are going to get 1 over 4 over x squared minus 1. We cheat again. Now we cheat again. 1 over. What is 4 over infinity? Remember this one? Number over infinity is 0. And I have a number. This is a horizontal asymptote. Y is equal to the answer to the limit, minus 1, is a horizontal asymptote. Let me show you what happens here quickly. Why quickly? Because it's exactly the same thing as the infinity case. Put it in, you're going to get the same thing. Infinity over minus infinity. You are also going to divide by x to the highest power. So you're going to get the exact same expression. And nothing changes because the method is the same. And then you're going to simplify. You're going to get exactly the same expression as before. And then you're going to cheat and you're going to get exactly the same thing as before. And you're going to get minus 1. Aha. So basically, doing the positive infinity and the negative infinity limit gives me the same answer, which means that, as a conclusion, y equals minus 1 is a horizontal asymptote. Now, I know what some of you are thinking. Because we got the same answer here for both the limit at infinity and the limit as minus infinity, do I have to do both every time, or can I do just one of them and I know that the other one is going to be the same? Well, it's a good question. And the question is, whenever the top and bottom are polynomials, which is going to be 90%, 95% of the functions we encounter, these two answers will always be the same. But if numerator or denominator is not a polynomial, like in the next example, then we're going to get a bit of a surprise. So let's actually take a look at example 4. Let's take a look at example 4. Exemple numéro 4. Now this one is a 3-star. 3 stars. Find all horizontal asymptotes for f of x is equal. What shall we have on this? Maybe something like root, aha, right? Not a polynomial. Or root 9x squared plus 2 3 minus x. Alright, so not a polynomial, actually a radical function in the numerator, polynomial in the bottom, but it doesn't matter. I don't have a polynomial in the numerator, so that is actually a little more challenging. I can't count on the fact that the infinity limit and the minus infinity limit will be the same all the time. So let us first check the limit as x goes to infinity of this guy. Now we've done similar problems before. I don't know if you remember. Like I said, when we do asymptotes, we are reviewing for the final exam, because the very first section of the course, remember, was on limits. So here's more limits. Oh yeah, the old is new and the new is old. Let us start with a good old cheat. Yo, infinity squared is infinity times 9 is infinity plus 2 is infinity. The root of infinity is infinity. Big surprise. 3 minus infinity is minus infinity. Once again, indeterminate. Now, whenever I have infinity over infinity, nothing changes. I have to divide top and bottom by x to the highest power. But the root actually brings about the level of difficulty that some of you may remember. So before I actually do this, before I divide top and bottom by x to the highest power, which by the way is what? X to the 1 here, x to the 2. Is it x to the 2? It's not x to the 2. It's not x to the 2. it's not x to the 2 because it's in the square root. And the square root of x to the 2 is not x to the 2, it's x to the 1. Huh. So I'm going to end up like probably dividing by x to the 1. But before I do that, remember that good old little trick thing that we did? Let us factor out an x squared from inside the root. Okay, so factoring out an x squared from inside the root. Some of you will remember this. Well, this goes 2 plus 2 over x squared. Don't do nothing to the denominator for now. Okay, what do we got? Limit as x goes to infinity of. Now I got a multiplication, which was the whole idea of making the previous move. The multiplication allows me to break this into the square root of x squared times the square root of 9 plus 2 over x squared, tutti quanti, tutti la familia, over 3 minus x. Now, the root of x squared, what do you remember this to be? The root of x squared. If you answered the absolute value of x, then excellent, good for you. The root of x squared is the same thing as the absolute value of x. Yes, ma'am. Yes, sir. 9 plus 2 over x squared, 3 minus x. Can I cancel the absolute value of x with x? I cannot. They're not the same. But I remember the definition of the absolute value of x. Actually, it is worth putting here. Once again, the absolute value of x is equal to x if x is positive, and it's equal to minus x if x is negative. Remember that. Keep an eye on this. It's popping up right here. X is approaching positive infinity, so that's going to be a very positive quantity. Because it's a positive quantity, I can replace the absolute value of x with x. So this is the limit as x approaches infinity of x root 9 plus 2 over x squared over 3 minus x. Okay, well, all of these three steps are prior to dividing top and bottom by x. Let's do it now. Dividing top and bottom by x. I won't have enough room. I'm, again, tossing myself in a corner. Let's do it over here. Those very small whiteboards are not very conducive to solving long problems like this. So, moving up here. Limit as x approaches infinity of, x the root of 9 plus 2 over x squared. I'm dividing this by x. Downstairs, 3 minus x. I'm dividing this by x, so x and x. That's an x right here. That is an x. Good. So that is an x. What is it that I get? Those two x's, they cancel out. Limit as x goes to infinity. Those two are gone. Those two, they cancel out. And I am left with the root of 9 plus 2 over x squared. And downstairs, I am left with 3 over x minus 1. All right, all this work. Time to cheat. Root of 9 plus 2 over infinity and 3 over infinity minus 1. 2 over infinity, you will remember, is 0. So that's the root of 9 over 0 minus 1. Hey, we have found a horizontal asymptote at minus 3. And that was a lot of work. Just to get this. So from this we get that y is equal to minus 3 is a horizontal asymptote. But remember, we actually did half of the problem. because there's supposed to be another limit that we have to evaluate, and it's the same as this, but going to minus infinity. So this will go faster because now we actually know the drill. So let me show you how this goes. So now, second part, I need to find a limit as x goes to minus infinity of the root of what we have, 9x squared plus 2. X squared plus 2 and 3 minus x. Okay, so all of the algebra will be the same. Okay, so all the algebra will be the same. Let me actually get to the point where I have the absolute value of x times the root of 9 plus 2 over x squared over 3 minus x. So all this same as before. Same as in the previous case of infinity. Same as before, no change. So I'm not going to go through the details. But now, x is approaching negative infinity. Remember the definition of the absolute value. Let me put it back in front of you one last time. It's equal to x if x is positive, but it's equal to minus x if x is negative. In what situation are we now? X is very negative, so absolute value of x now becomes minus x. So now this becomes minus x that I can actually replace the absolute value with. So minus x. So that's going to change a thing or 2 over 3 minus x. And now I can actually do my thing, which is, again, divide top and bottom by x to the highest power. So I got minus x root of 9 plus 2 over x squared. I'm going to divide this by x. And downstairs, I'm going to do the same thing here. X over x. Those two will be gone. Just like before, the only difference between the first and the second, the positive infinity and the negative infinity, is that here, instead of x, we have minus x. So, c'est quoi ça? What is that? Limit as x goes to minus infinity. This is gone. 2 over x squared. And this is exactly as it was before, not an iota of change. If you actually put in minus infinity into there, you're going to get minus the root of 9 plus 2 over infinity over 3 over infinity minus 1. Everything that's infinity goes to 0, so that's minus the root of 9 over minus 1. And that is now positive 3, as opposed to what it was in the case of positive infinity, where we actually got negative 3. In the case of minus infinity, we get positive 3. So the conclusion here is that y is equal to 3 is also a horizontal asymptote. So in this problem, we ended up showing that there were two horizontal asymptotes, one at negative 3 and one at 3. So the moral of the story, if you have a root, you are going to have to do both limits, the one at infinity and the one at minus infinity. If the top and bottom are standard polynomials, like they are most of the time, then the answer will be the same for both. All right? So I'll see you in class, and we'll actually do a little more of these. In the meantime, you take care.